Hey guys, welcome back to Cooker Chem Tutoring. I'm Austin. I'll be running through part 2 of problem set 14, molecular shape and VSEPR. Number 4, the molecules shown below smell like lemons. Draw the implicit hydrogens and write in the expected bond angles for each carbon atom. Okay, what is the relationship between these molecules? Are they isomers? If so, what kind, or why? If not, why not? Okay, so let's first determine implicit hydrogens. Now, if you haven't seen a stick structure like this before, it's used so often in organic chemistry. Okay, you have to get, if you're gonna take organic chemistry, you have to know exactly how to read this. So at every bend there is a carbon. Okay, these bends and the ends here as well are all carbons. So this end and this end as well are all carbons. Now one thing you need to know is that all the carbons, remember, every carbon can make up to 4 bonds, right? Whether they, consist of 2 double bonds, 4 single bonds, maybe a double bond and 2 single bonds, or whatever it may be. And so what we do is we assuming that if we see that this carbon has 2 bonds here and a bond here, then I'm going to assume that there's a hydrogen coming off the top there, okay? Because if I've got, let's say I've got this carbon right here, okay? It's got 1, 2, 3 bonds, and so I have to assume that there's a hydrogen there. Okay, so those are that's what they mean when they say implicit hydrogen. So if I look at this one right here, I've got another one right there. Okay, it's a carbon with a double bond here, a single bond here, so I have to assume that there's a hydrogen there. If you look at this carbon, however, it's got a double bond here, a single bond, and a single bond, so it actually doesn't have any implicit hydrogens attached to it. But this end here does. It's got 1, 2, 3 hydrogens because it's already got a single bond to another carbon down here. And you can kind of keep going through this and count them, but I'm actually just going to draw them here for you on this one. Not on the next one. I'll let you do the next one. It's pretty much the same though. So, but yeah, this is where these would be. Okay, remember, and don't forget these ends here. A lot of people think that or forget to do these ends, but those ends are another carbon. Okay, each of those ends are a carbon. So those are all the implicit hydrogens. Now they want to know the expected bond angles for each carbon atom. Okay, so if I look at these carbon atoms here and here that are all double bound. In fact, let me circle all the ones that are double bound. The reason is because they're all going to have the same bond angle. So I'm going to write, let me actually highlight these in a circle in a color. So I'm going to put orange. So here's one of them. They're here and here. Okay, so all of them, okay, are going to be those are a steric number of 3. Okay, now when I have a steric number of 3, if you look at this box that I've included over here, remember that if there's no lone pairs, it's just going to have a trigonal planar formation, and that would give me a bond angle of 120. So all of them are going to have a bond angles of 120. Okay, now there aren't any triple bonds in here, which means I will never, that I'm not going to get a steric number of 2 for any of the carbons. Okay, so what I'm just going to do is I'm going to label the other ones as this pink purplish color here. Okay, and that is going to be equal to a steric number, a steric number of 4, okay? Remember, each of these carbons up here had 3 other hydrogens, okay? And these carbons right here have a single bond here, a single bond here, and then 2 hydrogens down here, okay? So those are all steric number of 4. Now, when you have a steric number of 4 and you don't have any lone pairs, okay, that's going to be an angle of 109.5. Okay, so that's kind of how they want you to answer this question. Now, I'm not going to do this for the second structure. You're welcome to do that on your own. It's pretty much the same, though, but they do want to know the relationship between these molecules. Now, you'll notice that they're pretty much the same, with the exception that it's bent in a particular direction in a different part of the molecule. So now, I can see that, okay, I've got this part up here is all the same up until I get to right here, okay? In the other structure, this is actually pointed like this, right? You can kind of tell that this is going to be a cis-trans molecule. Now, remember, when we're looking at cis-trans and the difference between them, okay, what I'm going to do is I'm going to cut across this double bond. It's not going to be this double bond, okay, because it's not, oxygen is just on its own. It wouldn't have a cis or trans isomer, okay? So if I cut that and label this side 1, this side 2, I'm going to circle the biggest groups on each side according to atomic weight, okay? And so oxygen, if I look at hydrogen versus oxygen, or carbon and oxygen, right? This is going to be the bigger group, so I'm going to circle that. Now, if I look on this, on side 2 here, okay, I've got this whole big group here. So I've got a carbon, and then it's attached to, 2 hydrogens and a carbon and 2 hydrogens and a carbon and 1 hydrogen, and so on and so forth. And in fact, when you have structures like this, if you have a longer chain, that's going to be the bigger group, okay? Because they're both made up of carbons. So the only thing that differentiates them is how long the chain is. And the bigger the chain, the longer the bigger the group is considered to be. So then when we look across the bond, we see that they're on the same side of each other, okay? So this is going to be the cis isomer, and this is going to be the trans isomer, so they're cis-trans isomers, okay? Hope that made some sense. All right, number 5. Okay, we're going to be using this chart a lot here, okay? So this chart is not given to you on the test, okay? This is one I made. I actually got this template from a picture, but then I added these bond angles here for you. But these are things you're going to have memorized, okay? And remember that when we're looking at molecules with their angles, those angles are gonna change once we add lone pairs to them, okay? Lone pairs push these bonds downward further, okay? And so that actually affects our bond angles. So in this case, in the bent molecule, we would first assume, okay, maybe we're going to assume because the steric number is 3, it's going to be around 120. But because there's a lone pair, we're going to say less than 120, okay? So just remember the less than sign for anything past this point. And as long as you have these all in mind, that's all you need to know, okay? So 180, 120, 109.5, and then 120/90, and then 90. All right, so hopefully this will start to make some sense once we do these practice problems. Number 5 says, complete all of the following steps for each compound below. A, draw the Lewis structure, including all non-zero formal charges. Determine the electron geometry, the molecular shape, and estimate the value of the bond angle. Okay, so Lewis structures we've covered a lot in detail in previous videos, so I'm actually not going to show you the steps of doing a Lewis structure. I'm just going to draw the Lewis structure, and I expect you to know how we would have gotten there. Okay, so I'm going to put carbon here, and then I'm going to put chlorine up here. It doesn't matter if it was chlorine or hydrogen, because in this case, it's not chiral, so it's not going to matter. And it ends up looking the same anyway. So the electron geometry, okay, what you first need to know is the steric number. So look at the steric number. The steric number, that's steric number, I don't know if I've actually written this down, is critical to understanding this and a concept that we'll learn later called hybridization. Okay, the steric number is going to be super useful. But these numbers right here are the steric numbers that we're going to be looking at. So you'll always count lone pairs and bonds. So carbon has a steric number of 1, 2, 3, and 4. Okay, which means its steric number is 4. So when I look at the steric number 4, the electron geometry then is tetrahedral. Okay, tetrahedral. Okay, now molecular shape will only differ from electron geometry if there are lone pairs. If there are no lone pairs, it's exactly the same. Okay, so I know that there are no lone pairs on my central atom, right? There's no lone pairs on my carbon. So I'm going to say it's also tetrahedral, which means the angles are going to be 109.5 exactly. They're not going to be any deviation from 109.5. Okay. However, this will look different. We're going to do another example where this is actually going to look slightly different with a tetrahedral formation. So I've got chlorine, and I've got an oxygen up here and an oxygen down here. And I actually end up having 2 lone pairs on this chlorine. If you do this correctly, you're technically going to get a double bond between one of these oxygens. Now, in some classes, they may tell you that you need to keep a positive charge on this chlorine, and then keep 2 negative charges on the oxygens, because it doesn't want to expand its octet. I'm going to argue the other way. Okay, I'm going to argue that you do need to expand its octet to create this bond, because it will minimize its formal charge. Because if you look here, let me just rewrite this so you can see. This was a negative here and a positive here on the formal charges. This could come down here to make a double bond and minimize both these formal charges, and that favors both parties. So some chem professors will actually tell you not to do this, but I was taught to do this, so I'm going to do it. But if your professor says otherwise, just do what he says. And you notice that this is going to have a resonance structure, right? Because this double bond could easily have been over there. So I'm going to put brackets around this guy, put a negative charge, and I'm actually just going to do it down here if that's okay. I'm going to put chlorine, maybe just do it this way. Just pretend that that's the other direction, okay? All right, so there's my resonance structures. Now, electron geometry, I'm looking at steric number, right? So here's 1, 2, 3, and 4, okay? So that's a tetrahedral electron geometry. Now, the molecular shape could actually look different, right? The molecular shape is going to be bent, right? Because I've got 2 lone pairs where there would have been bonds. And so I'm actually going to put bent here. And what we do for this one, we actually put less than 109.5 for this one, to differ from trigonal pyramidal, which would be just less than 109.5, because it actually pushes things down even further. Okay, so this is going to be just less than 109.5. So that's kind of how you want to do these problems. Notice I've only included a few here. We're going to be doing some more down here, but I wanted to let you kind of practice on your own. First, just remember to do the steric number first, okay? And that's just based off of the number of lone pairs and number of bonds. Then determine the electron geometry, okay? And you'll have to have all of these memorized, okay? I've put the chart on here just to facilitate the teaching, but you're going to have to memorize this on your own. And then just recognize that your molecular geometry, if there's any lone pairs, is going to differ from that electron geometry. And you're going to have to determine what those angles are based on that idea. Okay, so number 6 here, I'm actually not going to look at the chart anymore, and I hope that you can look at your own chart, and we'll figure this one out together. Okay, so determine the molecular geometry of the following molecules using VSEPR and estimate the bond angles involved. Okay, so now they don't even care about the Lewis structure or the electron pair geometry. However, I am going to draw the Lewis structure to help us figure out what this would look like. So I'm going to assume that chlorine is the central atom, and I'm going to say fluorine over here and fluorine over here. Now, if you do this correctly, you'll actually end up getting 3 lone pairs on this chlorine. Now, when you get 3 lone pairs on the chlorine, you get a steric number of 1, 2, 3, 4, and 5. Okay, so steric number is equal to 5, which means if they were looking for my electron geometry, my electron pair geometry would be trigonal. Okay, bipyramidal is what it's called, pyramidal. All it is it's this line with pretty much a triangle around it, and then a bond here, and then technically if they were all bonds, they would be all around here. Okay, so that's kind of what it looks like. We call this the axial plane, and this triangle here around it, it's technically flat, and we call it the equatorial plane. Okay, so then I have to figure out based on the number of lone pairs what this actually looks like. And when you have a trigonal bipyramidal, what ends up happening is you end up getting the bonds on the ends here. So let me put the center atom here in the middle. And then the lone pairs actually end up surrounding the middle here, okay? And you actually create this linear structure because we don't look at, when we look under an electron microscope, we don't really see these guys. We just see this bond and this bond going out this way. And then we just say, okay, that looks linear, even though there are 3 lone pairs that surround this thing. So this is linear. Okay, so that would be our answer because they're asking for the molecular geometry, and by definition, then it would have an angles of 180 degrees. Okay, now this is a neutral molecule, and the negative charge we didn't indicate where the formal charge is, but this negative charge is actually on the chlorine, and which would mean the dipole. But actually, it doesn't affect the dipole. Sorry, the dipole actually points outward because fluorine is very electronegative. Okay, but you'll notice that these vectors cancel each other. Okay, so this is a neutral molecule. So I'm just going to say that this is nonpolar. However, we don't really talk about polarity when things are charged. Okay, but just notice that this is not going to be polar. Okay, all right, last one for number 6, BRF5. So I'm going to put BR. I'm going to put this here. Oops. If you do this correctly, you actually end up getting a lone pair around this bromine as well. So I'm going to do this here. Oops. Okay. Again, we're not going to do the process of drawing Lewis structures. I hope that the 4 previous videos that I've done on this can help you a little bit more with that. So now I need to figure out the steric number. Let me go ahead and erase this. Give me some room here. Steric number for this guy is 1, 2, 3. Remember the lone pair is 4, 5, 6. So that is 6. So the electron pair geometry is octahedral. Okay, octahedral. So in theory, my bonds would be 90 degrees all the way around. However, I do have this random lone pair here. So what that's going to do is kind of jack up my structure. So with steric number of 6, we still have an equatorial and axial plane, except we just have this kind of square shape in the middle. So we've got like a bond here, a bond here, a bond here, and a bond here. And we kind of just call it square, not square pyramidal, octahedral. So instead of trigonal bipyramidal, it would be like if it was like square bipyramidal type of thing. Okay. However, when we get a lone pair on this structure, it actually becomes part of the axial plane, okay? And this is why you have to memorize these because the rules will change for each one. So the lone pair will be down here, and it'll kind of push everything up this way. And remember, the angle for these were 90 degrees, and so pushing these in is actually going to make it less than 90 degrees. And that is consistent with a square pyramidal shape. So this is going to be called square pyramidal. Now, hopefully you can kind of see that in the structure. Okay, it actually, we've kind of got this structure here, and then the lone pair is kind of pushing everything up like this. So it doesn't look exactly flat because of this lone pair, but it looks enough like a square pyramid that we just say, or a square-based pyramid that we just say, okay, this is square pyramidal, okay? All right, last one, number 7. A 1995 gang attacked the Tokyo subway system, blah, blah, blah. Complete the Lewis structure by adding bonds and lone pairs as necessary. Okay, they want you to assign formal charges to the P and O atoms and determine the molecular geometry around the phosphorus atom. Okay, so remember that oxygen will always almost, well, at least in this case, is going to have 3 lone pairs, and we'll determine the formal charges here. It's going to have 2 lone pairs here because we're trying to fulfill its octet, right? This fluorine will have its octet there, and that's pretty much all that we need to know thus far. Now, they want the formal charges for the phosphorus and the oxygen. Okay, so the phosphorus wants, what does it want? It usually, based on the periodic table, okay, it's in the 5th group, so it wants 5. In this structure, it's got half of each of these bonds, so that's 4, so minus 4, that's going to be a positive 1. Positive, okay? Now, this is where I will kind of differ with some chem professors because I was taught to do this differently. But if you look at the lone, or the formal charge on oxygen, it wants 6 and has 7, okay? So that means it has a negative formal charge, okay? Now, when you have a negative formal charge next to a positive one, if the positive central atom can expand its octet, I have been taught to minimize that formal charge, okay? However, there are professors that will tell you not to do what I'm about to do. I'm making a double bond here, which will both minimize both of these formal charges, okay? It doesn't actually change the molecular geometry, so don't worry about that. But it does change what this would look like in terms of expanding octet or not, okay? So, if we look at the steric number then, looking here, 1, 2, 3, 4. Okay, so the steric number is 4, which means the electron geometry must be tetrahedral. Okay, and if it's tetrahedral, then I would, and there are no lone pairs, which I don't see anywhere here, then the molecular shape must be tetrahedral as well. Okay, which means that my bond angles are going to be 109.5 degrees. Okay. All right, I hope that was helpful. Mostly with these, it's kind of hard to kind of just show you this and then go through the shapes because it's really just much easier if you just memorize these on your own and then do a problem like this. So I would recommend, memorizing this chart with the bond angles, remembering that electron pair geometry and molecular geometry will be the same with when there are no lone pairs, but they will differ once you start adding lone pairs to these guys. On the thing that I have here, you don't actually have to know this last one, the 4 lone pairs one, as far as I know. But that's pretty much the general idea of VSEPR, okay, of determining shape. You're actually able to do a demo of this at home if you'd like. All you have to do is take a PVC pipe and then tie 6 balloons to a single string and then pull them into that tube. Pull it through the string through the tube, and you'll notice that it'll create, octahedral. If you pop one, it'll create a trigonal bipyramidal, or if you pop another one, it will go on and so on and so forth, because it follows the same pattern as electron pair repulsion, and so it'll create these shapes for you if you'd like to do that at home. All right, we'll see you in the next video.